A parallel universe is a proposed reality that exists separately from the one you are in right now, possibly with different events, different outcomes, or even different physical laws. The idea did not come from science fiction, it came from mathematics. Certain equations in physics, the ones that describe how particles behave, produce more valid answers than the one answer we actually observe. Physicists needed a way to explain what happens to those extra answers. Parallel universes are one attempt at that explanation. This matters because those same equations are not abstract. They are used every day in things like GPS satellites and secure banking systems. The equations work. What is still debated is what the extra answers mean. No human being has ever detected another universe directly. Everything you are about to learn is an interpretation of math that already works, not a new discovery pulled from a telescope. Here's what's actually happening at the foundation of this topic. Scientists are not arguing about whether the math is correct. They are arguing about what the math is telling us about reality. The first concept you need is the observable universe. The observable universe is the part of all existence that we can actually detect, because light from it has had enough time to reach us since the universe began. This matters because people often confuse "we have not observed something" with "it does not exist" or "it must be a separate universe." A satellite communication company only operates within a mapped, known signal range. If a satellite loses contact because it drifts outside that range, the company does not conclude a new dimension appeared. They conclude the signal has not reached that area yet, and they check the equipment before assuming anything stranger happened. Get this distinction wrong in a technical field, and you waste money troubleshooting a problem that does not exist. In the same way, the edge of the observable universe is a limit of light travel time, not evidence that something new begins there. The observable universe is simply the farthest we can currently see, not the edge of everything that exists. The next concept is the multiverse. Multiverse is a general term that gets applied to several unrelated scientific ideas, all lumped together under one word. This matters because treating them as one single theory causes real confusion when discussing the topic, and it causes people to think physicists agree on something they actually do not agree on at all. In finance, the term actuarial model gets used loosely to describe completely different formulas built on different assumptions, even though they solve different problems. Someone who assumes all actuarial models work the same way will misread a risk report, and that misreading can lead to a bad investment decision based on the wrong assumptions entirely. The same happens with multiverse. It is an umbrella term covering several distinct, unrelated ideas, not one single theory. The next concept is quantum superposition. Superposition means that a particle's properties are not fixed until the particle is measured or observed. Before that point, the particle exists across multiple possible states at once. This matters because superposition is not a guess. It is a confirmed, tested part of quantum physics, and it forms the experimental foundation for the more speculative ideas that come later. Quantum key distribution, a method some banks use to secure sensitive data, relies directly on this undetermined state. If an attacker tries to read the key early, the act of measuring it changes it, and the security system detects the intrusion immediately, shutting down the transaction before any data is stolen. Get superposition wrong when designing this kind of system, and a real encryption system fails silently instead of catching the intrusion. Superposition means a particle holds multiple possible states until something measures it. The next concept is the measurement problem. This is the unresolved disagreement among physicists about what actually happens the moment a particle is measured. This matters because this single unresolved question is the seed of one of the biggest parallel universe theories. A bank's fraud detection system flags a suspicious transaction as pending. Until a human reviews it, the outcome is real but unresolved. Once reviewed, it becomes one confirmed outcome, either approved or denied, and the account holder only ever sees that single final result. Physicists disagree about whether measuring a particle is more like that review, collapsing many possibilities into one, or whether every possible outcome actually happens, just in separate realities that never contact each other again. The measurement problem is the open question of what measurement does to a particle's undetermined state. The next concept is the many worlds interpretation. This is one proposed answer to the measurement problem. Instead of a particle picking a single outcome when measured, this interpretation claims every possible outcome happens, each in its own separate, undetectable reality. This matters because when most people hear parallel universe, this is the specific idea they mean. A construction firm designing a new building runs its structural simulation software through every possible load-bearing scenario before choosing one. If it committed to only one untested scenario and skipped that step, and that scenario turned out to be wrong, the building could fail under a load it was never actually tested against. Many worlds proposes something similar for reality itself. Instead of testing scenarios and picking one, every scenario becomes its own separate, real outcome. Many worlds is the idea that every possible result of a measurement actually happens, just in a universe you cannot access. The next concept is the inflationary, or bubble, multiverse. This comes from a completely different branch of physics, cosmology, which studies the origin and structure of the universe as a whole. This model proposes that the extremely rapid expansion of the early universe could have produced separate regions, or bubbles, each becoming its own independent universe. This matters because it is often confused with the quantum multiverse, even though it comes from entirely different physics and rests on a completely different set of equations. A manufacturing plant running several production lines from one shared batch of raw material will end up with lines that diverge over time, even though they started from the same source. A defect in one line does not mean the entire batch was always doomed, and shutting down every line over one bad result would waste time and money unnecessarily. The bubble multiverse works on a similar principle at a cosmic scale, separate expanding regions branching from one shared origin. The inflationary multiverse proposes separate universe bubbles forming from the rapid expansion of the early universe, and it has nothing to do with quantum superposition. The next concept is the string theory landscape. String theory is a framework that attempts to describe all fundamental particles and forces using tiny vibrating strings instead of point particles. Its equations allow for an enormous number of possible universes, each with different physical constants, different strengths of gravity, or different numbers of dimensions. This matters because it shows that parallel universe does not always mean different outcome of the same event. Sometimes it means an entirely different set of physical laws running underneath everything else. A structural engineer testing a bridge design under many different material specifications, different steel grades, different concrete mixes, is searching for which specification produces a stable structure under real load. String theory's landscape works the same way mathematically, testing which set of physical constants could produce a stable universe instead of one that immediately collapses. The string theory landscape describes an enormous range of possible universes, each running on different physical rules. The next concept is the anthropic principle. This is the reasoning that any observers capable of studying the universe must, by definition, exist in a universe capable of supporting them, regardless of how many other universes might exist that cannot. This matters because it explains why our universe appears finely tuned for our existence without requiring that it was designed that way. A job applicant only receives interview invitations from companies where their resume happened to match the requirements. That does not mean the position was designed specifically for them, and assuming it was would lead them to badly misjudge how competitive the process actually is. It means mismatched applications simply never generate a callback. In the same way, we only exist to observe a universe that supports our existence, which does not prove that universe was designed for us. The anthropic principle explains why our universe looks suited to us without requiring that anyone tuned it that way. The next concept is falsifiability. This is the requirement that a scientific claim must be testable, meaning there must be some possible experiment or observation that could prove it wrong. This matters because most parallel universe theories currently fail this test, which is exactly why many physicists question whether they qualify as science at all. A financial auditor reviewing an investment projection that cannot be checked against any real, verifiable data will reject that projection, no matter how confident it sounds or how impressive the presentation looks. Accepting it anyway risks real financial loss when the projection turns out to have no basis in anything checkable. Physics applies the same standard. A theory that cannot currently be tested does not get treated as confirmed, no matter how elegant its math looks. Falsifiability requires that a real experiment could, in principle, prove a claim wrong, and most parallel universe theories cannot yet meet that standard. The final concept is the difference between the simulation hypothesis and a parallel universe. The simulation hypothesis is the claim that our entire reality is a computer simulation. This matters because it gets mentally merged with parallel universe theory constantly, even though the two ideas answer completely different questions. A single video game rendering its world on your screen is one simulation. Two separate servers running the same game at the same time are two separate, parallel instances of that simulation, and a problem on one server has no effect on the other. Those are two different concepts, one about whether reality is simulated at all, and one about whether multiple realities exist side by side. Confusing them muddles both discussions and makes it harder to follow either one clearly. The simulation hypothesis asks whether reality itself is artificial, while parallel universe theories ask whether more than one reality exists, and the two questions are not the same. Let me show you exactly how this works when several of these ideas apply to one real task at once. An engineer is designing a new encryption system for a bank's mobile app. The system relies on quantum superposition to generate secure keys, since the key does not hold a fixed value until it is read. Whether reading that key collapses it into one final value, or whether, as the many worlds interpretation proposes, it branches into separate outcomes in separate realities, is exactly the unresolved measurement problem in physics. The engineer does not need to resolve that debate to finish the project. Because of falsifiability, only the testable, repeatable mathematics gets built into the actual product, not the philosophical interpretation behind it. In this one task, four separate ideas, superposition, the measurement problem, many worlds, and falsifiability, are all active at once, and the engineer builds working, secure technology that protects real customer data without ever needing to settle which interpretation is true. Here's what people most often get wrong. People confuse a scientific parallel universe with an alternate timeline from a movie or show. Fiction uses alternate timelines as a storytelling device, while physics uses the term to describe a specific, debated mathematical implication. These are not the same claim, and treating a film plot as scientific evidence leads to a distorted understanding of the actual physics, one that falls apart the moment someone asks a real physicist about it. People also assume that because quantum mechanics is real and tested, it must prove that other universes exist. Superposition is confirmed. Many worlds is only one interpretation of what superposition means, not the only one, and not a proven fact, no matter how often it gets stated as settled. People also treat "we have not observed something" as the same as "a separate universe exists there." The edge of the observable universe is a limit caused by the time light takes to travel, not a boundary where a new universe begins. People often assume the string theory landscape is settled science, when string theory itself has not been experimentally confirmed, making its landscape an additional, further step removed from proof rather than a confirmed catalog of real places. Finally, people merge the simulation hypothesis with parallel universe theory simply because both sound like science fiction, when the two ideas are addressing entirely separate questions that require entirely separate evidence. This understanding has real, practical use. When you see a headline claiming scientists have proven parallel universes exist, knowing the falsifiability issue stops you from reacting to hype that outpaces the actual evidence and saves you from repeating a claim that will not hold up under scrutiny. When evaluating a pitch involving quantum computing, understanding the difference between confirmed superposition and speculative interpretation helps you separate genuine engineering progress from marketing language designed to sound impressive, which protects you from overpaying for a product based on exaggerated claims. When watching a documentary or listening to a podcast on cosmology, recognizing which specific multiverse theory is being discussed prevents you from misunderstanding the actual claim being made and stops you from walking away with a garbled version of what was actually said. When discussing the topic with a technically minded coworker or friend, being able to name the specific theory, many worlds, the inflationary bubble multiverse, or the string theory landscape keeps you from sounding either uninformed or overconfident in a conversation where precision actually matters. You can now separate the different theories that all get grouped under the single word multiverse instead of treating them as one idea. You can identify which claims in a headline or conversation are confirmed physics and which are unproven interpretation. You can explain why none of these theories are currently testable and why that distinction matters when deciding how much weight to give a claim. You can now spot the difference between a mathematical possibility and a scientific discovery, and you will not mistake one for the other again. You now have the understanding of this topic that you should have been given the first time you encountered it.